Hydroboration of Alkenes. Here's borane. It's got trigonal planar geometry, but the most important feature is its partial positive. And it's got that partial positive because boron only has 5 protons. It has a hard time gaining an octet. And in fact, all of these protons have partial negatives, which is something one does not see very often, but there it is. And this is also why it's got very bizarre chemistry. Borane normally forms dimers where they share hydrogens between themselves to get closer to something that would be an octet. But we care about this because what we're intending to do is a hydration reaction, which is adding water to a double bond essentially. And normally when we do that we get Markovnikov orientation. The whole point of this is that it gives us anti-Markovnikov orientation. So let's see how this is done. Here's an alkene. Here's our weird boron. Here's THF. THF is a solvent that we almost always see with boron, and it's a cyclic ether. And essentially what it does is it makes a bond to borane. And what it does is it helps dissolve it in different liquids. Borane is a gas normally. And a lot of times we're dealing with liquids, so we don't want to deal with the gas. Also, borane is explosive and it's toxic and it's just all around really nasty. So this really helps make it safer, but also it's just more practical to use it this way. So that's that. Borane adds to the double bond. It's important to remember at this point that borane, the boron, has a partial positive charge. So this partial positive, it's going to be attracted to the carbon that has more electron density. Remember, in organic chemistry, we always have to think of it from the perspective of the electrons. It's a massive, never-ending battle for electrons. So we've got 2 carbons here that the boron could go over. And this left one is bonded to 1, 2, 3 carbons. This right one is bonded to 1, 2 carbons and a hydrogen. So which of these 2 carbons is going to have slightly more electrons about itself? The one on the right, the less substituted one. Because the less substituted one is only fighting with 2 carbons of equal strength to itself, and it's fighting with a hydrogen that it is weaker than, so it'll be able to draw more of the electrons from the hydrogen to itself. Where this carbon over here, it's fighting with nothing but carbons, so it's going to have a harder time drawing electrons to itself because it's fighting against adversaries of equal strength to itself. So the boron goes over the less substituted carbon with more electrons. Normally when we've had a hydration reaction, the alcohol has ended up on the more substituted carbon because that's where the carbocation is formed. But here no carbocation is formed. So this partial positive is going to be attracted to the slightly more negative carbon. And here is the end result. Here's a boron, and here's a hydrogen. And the hydrogen is on the more substituted carbon, which is the opposite of what's happened in our other hydration reactions. And all that's left to do is just to remove the boron and replace it with an alcohol. And this is done with peroxides and hydroxide ions and water. And it just replaces it. And here's our end product. This is why we care about it. So we'll have a look at this step right here in more details. It's interesting. So here we've got our boron bonded to 3 hydrogens. And essentially what we're going to have a look at right here. So this is just a shorthand of this whole thing right here. Boron bonding to an alkene. Boron, hydrogen, but this boron still has 2 other hydrogens, and what it can do with those is that it can bond to other alkenes. So it can bond with the same one. So now it's got 2 of these arms. So now essentially it's bonded to 2 of these things right here. And now it's got 1 hydrogen left. It can do the exact same thing. It can bond to another alkene. So now we've got a boron, and we have 3 carbon arms. 3 of whatever carbon alkene we had. So this happening 3 times. Now we got to look at our peroxides. Create an ion. This is incredibly negative. And what it's going to do, since this has a partial positive still, it's going to be attracted to it. This has a negative, I forgot that. Oh, and I forgot the electrons over here too. What do you know? Just forgetting everything. So it's going to be attracted to the partial positive. Temporarily, this is a transition stage here. Temporarily, boron is going to be bonded to 4 things. Now that's going to have an octet now, but it's only got 5 protons, so it's not going to be able to hold on to it forever. In the middle of the transition stage, its protons are overloaded. It's got to lose something. What happens in the transition stage, as this oxygen binds to the hydrogen, or to the boron, one of the carbon arms is going to be attracted to the electron density over here on the oxygen, and at the same time, as this carbon is going towards these electrons, then these electrons over here, that this oxygen is bonded to this other oxygen, are going to start to come loose, and this oxygen is going to be able to pull them away from this other oxygen. So in one step, this carbon group goes to the electrons on the oxygen, now that it's nearby. The electrons on the backside of this oxygen leave, and what is left is the boron bonded to the oxygen now, which is bonded to the carbon arm. So it just put an oxygen between itself and the carbon arm, and then the hydroxide ion is able to leave. And as with this step where it happened to the other arms, it can continue on this same thing. The peroxide can come in and shift over the arms. And this is what the remainder is. Boron, oxygen, carbon. Boron, oxygen, carbon. Boron, oxygen, carbon. So now we can see we're almost at our product. This is what our product is right here, but it's just bonded to this boron. So we got to get rid of this somehow. This is how it happens. Get the hydroxide, it comes back. It forms something very similar to what is formed in the previous step, where now the boron has 4 bonds again, and it cannot hold on to all of them. One of these oxygens will be able to withdraw the electrons. So there are too many electrons around this boron, it can't hold on to them, it's only got 5 protons. Oxygen is able to withdraw electrons from the boron, and it goes off on its own. So now we have boron, oxygen, hydrogen. And this step can repeat itself. Then we have carbon and oxygen, and it's an ion. So whenever it runs into a water, it's just going to take a proton from it. Runs into water, takes a proton from it. Now we have our final product. And it can continue on for the other arms. So we will get 3 from 1 boron. Now here we can see that it's pretty reasonable, just from an electron perspective, that these would want to be replaced by oxygen and hydrogen. Here the oxygen is fighting with carbon and boron for electrons, where if it's replaced with hydrogen, it's going to be, the oxygen will be more content because it's getting more electron density from the hydrogen, so it's not having to strain against this boron so much. So it's pretty reasonable that that should happen. And the result, of course, again, is an alcohol, which is this up here. But an anti-Markovnikov orientation.